So since this distance right here is the opening of the slit, the single slit D, times the sine of the angle, we're looking at this distance, d sine theta, to see if d sine theta is of the, I'm sorry, I got my notation backwards there, to see if d sine theta is equal to lambda. When d sine theta is equal to lambda, it means one more whole wave has been able to be constructed right here, which will interfere positively with this wave up here. And therefore, we get the distance to the next maxima, and that will give us the angle to the respective maxima that we have for a single slit. Let's look at interference between two nearby frequencies. Interference between two nearby frequencies, F1 and F2, results in an average frequency that has beats. So what is it that happens when we have two nearby frequencies? Let's assume we have a frequency F1 and another frequency F2. And if I think about these two frequencies, this one's going to go along, and they may have started out in phase, but one is a higher frequency. Like let's say this one right here is a higher frequency. So always they're going to get out of phase. What is it that you actually hear? Well, I drew this a while ago. You hear a large wave at first, and then you begin to get interference, and then it builds up, and they get back in phase again. And so if you think about the envelope of this wave, you're going to actually hear a wave that gets louder and softer because of this envelope. And at the same time, you hear a wave here that is the average of the two frequencies. So when you hear F1 and F2, you're actually going to hear 1/2 of F1 plus F2. And you're also going to hear 1/2 of F1 minus F2. You're going to hear the average of the frequencies, and you're going to hear the difference of the frequencies. And this is going to be the amplitude. It's going to be a product. I put a plus sign there originally. This is a product of the two. So at a frequency that is the difference of the frequencies, you get an amplitude that gets larger and smaller, but what you hear is the average frequency. So you never really hear two frequencies that are exactly the same. And say you're trying to tune a guitar, and you have a tuning fork, and that might be F1, and you pluck your guitar string that's supposed to be that frequency F2. And they're going to be slightly different in their frequencies. And so you're going to hear a sound that's something like, and that frequency that you hear is the average frequency, but that beating is a frequency multiplier that is 1/2 of the difference of the two frequencies. But since this 1/2 of the difference gets larger here and gets larger again down here, this increase occurs twice each time. So we can ask, this is the frequency here, frequency heard, and this is the beating. Beating is called the loud and soft oscillation. So this beating is the amplitude that multiplies this frequency here. And you'll notice that the frequency of that beating is 1/2 F1 minus F2, the difference of the frequencies, where we take the large frequency first. You also recall this is going to happen twice for every oscillation. So the actual frequency of the beating, like that, is a frequency F1 minus F2. What is the period of that frequency? You recall that the period is 1 over the frequency. So it's going to be the reciprocal of the difference of the frequencies that you have. And I've written that here as T is equal to 1 over F1 minus F2. And that can be used to tune one instrument against another as a standard. Because if you wait for a very long time, it means the frequencies are very close and you do not hear that beating. So you tune the second instrument to this standard so that this beating lasts longer and longer and longer. And then the two are in phase, to have the same frequency with one another.